Good. Good morning. How are you guys? Everybody up and running? Yeah, running. That's good. That's good. Welcome to our presentation. Let's quickly do an intro. I have two co-speakers with me. So my name is Mario. I'm working at the global Hilti headquarters in Liechtenstein. Very big city, very big place, you know, country. So it's probably 8 miles wide and 15 miles long, kind of, right? So.
That's a nice castle.
Yeah, there is a nice castle. Actually, you have been there once, no? Or you have seen a picture? Okay. Cool. I'm responsible for all structural engineering software around the globe. And I'm happy to be here with you in order to talk to you about some workflow challenges we see in the industry and some solutions to these challenges. With me, I also have David.
Hello, everyone. I work as a product engineer in IDEA StatiCa. Our headquarters is in Brno, in Czech Republic. It's located in Europe. And today, I will explain for you CBFEM method.
And then we also have Anthony with us.
Hi, so I'm Anthony. I am a structural engineer at Dig & Kolb Engineers in San Francisco, and I'm going to be talking about a few real-world use cases of this new finite element approach with the PROFIS software.
For us, it was important not to, as manufacturer or as software vendor or whatever, just speak to you. We also wanted to invite kind of a engineer that is using it on a case-by-case basis in order to make sure that the stuff is not too much on the theory, that we can also talk about practical examples, right? Good. Let's get started. So I want to start with this quote. Please take kind of 20 seconds to read it. Why do I put this up? I've been already presenting at AU, I think, 2 years ago, and it's always difficult, right? I don't want this to be a one-way show, right? I want to have an interaction with you. I will ask you some questions. I would really want you to contribute and have a lively discussion with us. And for me, actually, I took a 20-hour trip to come over to here in order to talk to you and also get some feedback and talk to you on your problems and so on. So please, interact with me. If you have questions, stop me. If I have questions or if I post questions to the room, please feel free to answer. There are no wrong answers, right? Everything is good. Good. Let's start here. We have done some extensive research on the workflow in the AEC industry. I'm a structural engineer, and I used to practice some years ago, and I have experienced this pain by myself, right? So that's why we started investigating and trying to understand how is the industry currently working. Let's just take now a project. There is an architect. There's an owner that appoints an architect or whatever. Architect is coming with the shape of the building, right? Then there's the structural engineer doing the superstructure design. In these days, I would say mostly with a structural engineering software. You name it, there are a lot of different packages around. And then once this is done, the superstructure, the sizes of the beams and columns and everything is defined, that's fine. And then when it gets into more detailed engineering, all the details like connections and the base plate and these things need to be designed. As Hilti, we focus on these steel to concrete connections because that's also where we have our products, our anchor bolts, our stuff available. So we focus now on this base plate connection. So you need to do quite some checks. You need to size the base plate. You can do this probably via Design Guide 1 or whatever. You need to design your anchors. Hopefully you're using our software for doing so, probably also competitor software. You need to design the concrete underneath the base plate. You need to design the weld. So there are a lot of different tasks. And so far, these tasks are all kind of isolated. So if you say you do base plate design with DG1, so you need to transfer the loads from the superstructure design manually. It's normally printed out. And then you need to read the report, look which load combination is the governing one, and so on. So that's a manual and a slow process. Once you did the base plate design, you probably start with the anchor design. You might find out that there is no solution. Then you need to go back to the base plate design and probably size your base plate differently. So there are a lot of manual steps and a lot of iterations needed. At the end, for sure, you want to document everything you did just to make sure that you're on the safe side and you can basically put everything down. Then, once the design is done, let's assume we have found a solution. We now need to put it into the detailing. So what happens today, or what we have seen so far is, okay, some design reports, some sketches are basically handed over to the draftsman. The draftsman needs to, the geometry of the base plate needs to enter it again into his whatever Revit or Tekla or whatever software. So again, a manual step where data would have been already available in an electronic way, but the industry just prints it out and does it again because these systems are not talking to each other, right? Next one is then bill of material, order placement, and so on. And the final thing is bringing the points to the job site, really understanding, okay, here I need to drill a hole to install an anchor and so on. And this is in these times still in a lot of cases done manually, right? So that's more or less the process how we have seen it. That's what we have confirmed with quite a lot of customers. And in the end, the summary is it's slow, it's a lot of manual work, and it's error prone. And in case of a change, let's just assume the owner is a very nice guy, and once you have done all your work, he decides, actually, no, I don't want a column here. Then basically you need to go back and walk through this tedious process once more, right? And so what we have seen, there is a lot of time lost and a lot of productivity killed just with this process. To summarize the main pain points. If you're using structural engineering software, there are normally you put in the live load, dead load, wind load, seismic loads, and so on. And as you know, there are a lot of load combinations sometimes, right? So which one is now the governing one? That's a tricky question because there is no clear answer. It might be this one, it might be that one, and it might be even the case that for the base plate, this one is governing, and for the anchor, this one is governing. So it's tricky. So the first pain point is you need, out of the list of load combinations, you need to select one or more you want to design for. And that's tricky, and the likelihood of selecting a wrong one is pretty big. Different methods and tools to be used. In the end, there are a lot of, as we said earlier, there are a lot of manual data transfers and a lot of manual steps in behind. There is one more risk. If you're using different software packages or formula-based assumptions and software packages, there might be even different assumptions behind for some checks. We will come to that in a minute because ACI has some requirements some AISC guidelines do not have. So there might be even some different assumptions behind, and you might basically tap into one of an issue that you could somehow avoid. Tedious, error prone, I think we have talked about. Significant effort required to implement changes. That's also something we talked about. The owner doesn't want to have a column there. You need to go through this tedious process once more. So that's how we see it. Now I would first hand the word over to Anthony to also share a little bit his understanding and his experience. Probably he can add some more problems. I have a flip chart over there. If you have some more problems, please speak up. I will basically take then some notes, and during the presentation, I want to always try basically then to also refer to your problems you basically bring up here, okay? Anthony, please.
So, thank you, Mario. So you hit on pretty much the main topic here, where it's very tedious to go through all the different load cases and to go through and basically manually enter all of your data from your favorite analysis software into whatever you're using to design your anchorage. The other thing I'd like to add to that is sometimes I know we'll do some sort of envelope case to try and get the absolute worst that we can, and that also creates much larger loads than you'd necessarily need to design for. Especially for me with seismic loading, taking the maximum seismic load in one direction, the maximum seismic load in the other direction, and trying to design for that whole envelope to try and simplify your design could end up with a much larger base plate anchorage than you really need.
Okay. So it's basically over-designing, right?
Yeah.
Good. Now I'll turn it over to you. Who is first? Tell me. You know I'm prepared. I already expected this. So, remember Bill Gates' quote at the beginning? Please, help me. If you see some other things, if you can confirm what we say, just please let us know. And in order to get it started, I have here something for you, you know? Have you ever heard of Switzerland? There are some famous products in Switzerland. One of it is the Swiss Army knife. And here I have one, and actually it's not a Chinese copy, it's a real Swiss Army knife. So please, guys, speak up. If you confirm what we have shown, if you have a different opinion, just let me know. Please speak up. Ah, okay, I have two, okay. He was first, okay, good. Tell me.
Getting information out of the design software into our detailing software, such as Revit, without having to put that information down on paper, hand it to someone else, and then put it back in the computer. Like, why not have it where it's linked through the computer?
So you're talking more about geometry information, things like that?
Base plate size, anchor bolt size, embedment,
Yeah.
all that.
Thanks a lot.
Yep.
Hope you like it. Let me tell you can already start, and I will put down the note.
So, in my line of work, essentially the problem that I see is that the structural engineer, me, we have a global analysis model, be it in SAP, ETABS, RISA, so full building model. We need to look at the base plates. We have maybe hundreds of combinations, like the gentleman here saying, if you do an envelope load, you're essentially taking the worst of the worst of the worst, which doesn't realistically happen, right? The solution that I find is you need to check everyone, and then at the end, see the sizes that you get, and then envelope the size of rather than envelope the loads. The problem is getting the loads from ETABS or SAP or RISA into PROFIS, for example. There isn't one, like you push a button and it'll convert it into an XML or something like that that will input all these loads and you go through them.
I'm so happy you're here.
Me too.
And I can tell you, there is a solution. I will show you in a bit.
Okay, I'd love to see that.
Thanks a lot. Anybody else?
It seems easier to use the overstrength because it's quicker. And I think versus trying to find the ductility in the base plate and look at fused proof. You can use standard size big loads with a redundancy from an overstrength policy.
Okay.
It's a simpler approach, but at least larger base plates, bigger.
Okay. Thank you. Anybody else? No? Okay. Good. At least I was successful already for the first challenge for me in order to get you going. That's good. So let's talk about what we have. And it will probably, it will solve the two things over here. This ductility topic I would love to discuss a little bit more after the session, just for us to understand, to really understand in detail what would you require and so on, for us to then think about and see what we can do with it, okay? So, what we can do, and later on I will show you a video, our new software is able to take loads from SAP, you mentioned SAP 2000 and ETABS, right? Is able to connect with them and kind of in the background grab data. You can select which load combinations, which node you want to have, and then in a digital way transfer the 100 load combinations over to PROFIS, and just by hit of one button, PROFIS will calculate all 100 within probably less than a second, and will basically give you the one that is worst case for you.
How much does it cost?
We will come to that as well later.
Take my money.
Please.
Is it connected to Global RFEM?
Yes.
Yes.
Yes. We also have global RFEM, we have SAP 2000, and we have ETABS. And we are looking, Start Pro is another thing we are going to bring very soon. But even if your software is not on the list of the ones directly supported, we have also a second way of allowing you to transfer the data. And so every structural engineering software that is able to export your nodes, forces, or reaction forces on the node to Excel. From Excel, you can then copy-paste it to Profis. So it's probably 10 clicks more, yes, but in the end, there is also a way to bring hundreds of low combination from, I don't know, Strand 7 I heard recently, or some other software package where we might not invest the money to do a direct connection, but still, you have the chance to export it to Excel, and then from Excel, just copy-paste, Control-C, Control-V, and then everything is there, and you can run your whole calculation. Okay? Then, once the loads are in Profis, we have heard a lot of feedback, and I'm working with Hilti now in the software area for structural software for 8.5 years. And I can tell you I have gotten hundreds of emails and hundreds of complaints, also when visiting customers and specifiers, engineers as well around the globe, that, Hilti, you do anchors, that's great, but I need also the welds, I need also the base plate, and so on. And so what our new software also has is basically all design checks are in one software, and then you can click a design report that will basically give you a documentation of all design checks in one go, right? No need to transfer data from hand calculations and then finally copy-paste the design report together, so everything will be there in one. And the next thing, and now we are coming, I'm not sure who was it, your topic with Revit. So let's assume you have selected your base plate size, you have selected your weld seam, you have selected your anchor position. Then by click of 3 or 4 buttons, you can then export the stuff into Revit. It's not yet available, but it will be available in early 2020, meaning in the first quarter. And then you can really solve your problem and be able to transfer all geometry, anchor bolt size, and weld seam, and so on into Revit.
Will you be including in that smart tag, where we can just like tag based on material or something like that and get the information?
For the time being not, but I think that's a great idea. I've also taken on, and probably after the session I would like to talk to you on this a little bit more. Because, you know, we are also always looking for new ideas and things where we could improve your design workflow and your process. Good, and we have talked now about Revit. Also there is kind of, for some software packages, we will have a direct integration where we really make sure that it works in a very seamless way. There is also the second layer, kind of, like we had the Excel for the structural engineering software. So there we have this called BIM CAD library where you can export it to an online web service that is basically then creating DWG or IFC or whatever, and then the information is there. The only difference is, in this case, it would be blocks. In the Revit case, where we really use Revit, it will be native Revit objects, right? That's the only difference over there. Good. Anthony, probably you can also speak a little bit about how you guys are using these new functionalities.
Thank you, Mario. So I know that in our office we had a Hilti representative come and talk to us, let us know kind of about some of this early integration stuff from our analysis softwares in, and have had great success using Excel so far. I think that at that point that was all that had been implemented. And I know several engineers in our office have really used that to further their designs, cut down on any sort of excess, and really be able to quickly check 10, 20 load cases, and I've used that and found it tremendous.
Good. Comments, questions so far? All good? Okay. So in the end, we just now want to show a video because, yeah, talking about it is always great, but let's just, I think it's 1.5 minutes, let's just watch the video and just see what the new functionalities can do. I think it should start now. So in this case, we are now in robot, yes, exactly, robot. You have your structural design, you have basically your support nodes. Then you will log in, then Profis Engineering will in the background connect to robot. And if you hit this button, you will be able, out of robot, to see all your load combinations and your nodes. and then you can select the ones you want to import. And what you will see down here, now the different load combinations are there, and the one with bold letters is the one basically that has the higher utilization. And you can, I think the limit is currently some 100 load combinations, right? And that's fine. That's now our new finite element or component-based finite element solution. We will come to that, and we also have an expert with David here to really make sure that you answer all the questions. But there, essentially, you can design all details, including welds, including the concrete underneath the base plate and so on, and then really check also the stresses, deformations, and all this kind of stuff. On the right-hand side, in our PROFIS engineering software, you always have the results. So the first thing is anchor design, then plate design. We also do the hole bearing check and so on, the weld design and the concrete design. And at the end, all of these design checks you can check in more detail. And finally, you can get a PDF report with all code references and all this kind of stuff, just to make sure everything is properly documented and you have everything available. So now you have designed your anchors. Let's now look at how you bring it into Revit. So that's a Revit model, very simple one. How this will work, there will be on Revit, there will be a plugin you can install. And this plugin we offer you will be able to read your PROFIS engineering file. So you just say, okay, I load now this, I called it Autodesk University example, okay. I load it, and it will now automatically fill all the parameters that are needed for a standard Revit baseplate connection. You click the button, and now your baseplate is there. You see the anchor, you see the hole. We are also now working in order to add the weld seam and so on. So all this geometry is there, and as you can see here, it's not a block, it's really standard or really native Revit content, right? So that's what we have been working now for quite some time, but now I have already seen the first prototypes, and on the development side, we now need to do some massive testing efforts just to make sure everything is working the way it should, and in Q1, this will be then available for our customers now. Okay? You just stop me if there is a question, or he wants a knife. One. Yes.
I assume because you have him with you that there's some limitation with this.
There's some?
Limitation with the Hilti design and connection.
No, what we are expert on, Hilti, we are experts in anchor design and all this kind of stuff. We have people working in the ACI committees full-time and da-da-da-da-da. So anchor design, we know everything, right? Structural steel design is kind of not our home base, right? So, exactly. So we looked at what's available on the market, and then we found this very innovative component-based finite element method, which is unique around the globe. And then we decided to partner up with IDEA StatiCa, who is kind of the father of this method, right? And we have then brought their method into our software. That's basically the split, how we do things.
So they're the engine behind your finite element analysis?
The theory and the concept behind, that's basically what is about this component-based finite element method, which is a pretty unique thing, yes.
Why don't you use just IDEA StatiCa instead of
Because in the end, IDEA StatiCa, the IDEA colleagues are the expert in the steel-to-steel connections mainly, right? And with our testing labs spending 250 million every year on research and development on the connection to concrete, on this connection design, we have much more data, we know much more, and so we bring the two things together, right? Our expertise on the anchor design, how an anchor is really behaving, spring stiffness and such things. We have done extensive testing for our anchors, we know all of that, right? And this is our input in the model. You could always simplify it, but your results will be much less accurate, right? So we bring the expertise from both sides and the method together in our software.
another question, in the robot you have the steel design and door which can enter, there you can do the base plate analyze and also consider the foundation. What's the difference between those two?
we will come to that because I think once we show how fast and how easy it is to model the base plate and get it designed, you will see the difference. But may I park this question? I will get back to you on this question, okay? Thank you. Good. Then let's go ahead. How do you guys design base plates? Please tell me. I would be interested how you said now SAP, you said robot? Exactly, so you do model really the plate and then all the stuff you kind of do some support assumptions for the anchors and you apply a material law and then that's how you do it, right? Okay. Okay. Okay, good.
You can do it both ways. You can either do it by the steel design solution if you have a steel connection.
Mm-hmm.
If you have more complex, then you can analyze it as a shell objects.
Mm-hmm.
You know, using supports as connections and build up more complex.
Yes, I will come back to this.
You don't have the code checking in that area.
Exactly, you don't have the code checking, and if I tell you here in this software, in 1 minute you have the results. If you model it, and if you need to find models for the concrete, bed of springs, you need to think about your anchor stiffness. Exactly, yeah. Good. Other colleagues, how are you designing base plates?
Well, where I come from, depends on the age of the engineer.
Okay.
So the older they are, the thicker the base plate. You put in an inch.
Good.
And, you know, that's your design.
What's this famous line of age? Am I above or beyond or below?
I'd say it's like 50.
Okay, I'm below.
Yeah, so you've got that, then you've got the design guide 1.
Mhm.
So everyone has their own secret sauce spreadsheet, which is terrible because it means that the same geometry, same loads give 15 different answers.
Okay.
So, and then you've got, you want to be PhDs like me, or if necessary, we'll go into FEM, and then we have to explain to our process how this magic works.
Okay.
And we end up with the inch-based plate.
Good. Thank you. Somebody else? Well, you already covered probably most of the things, right? What I thought about before. So experience is for sure a big thing. Design guide 1, also formula-based, that's clear. Excel spreadsheets, tricky somehow for some, I would assume for some simplified cases it would work, but yeah, you need to always maintain it and da da da. And then finite element for some more advanced experts kind of, because this finite element has somehow the touch of being PhD. You need to have a PhD or probably even better 2 in order to use it, right? So good. I think, Anthony, is there anything else you want to add, how you design base plates?
That's pretty much all of them, yeah.
Good, so one person answered all of the points, that's good. If there is anything else, just speak up, please. Good. You mentioned Design Guide 1, right? Design Guide 1 is a solution, formula-based, easy to execute for some simplified applications, right? So let's just say small bending, small moments, large moments, probably tensile, but only if the tension force is in the center, if you have 4 anchor bolts and so on, right? So there are also from the profiles, there are some limitations to Design Guide number 1. But still, it's probably, the market research we have done is probably the most common method currently in the US. So also this, we have listened to our customers, right? And we have also created, in the new software, there is also a Design Guide 1 option available. So you just select. Here you can select basically your AISC Design Guide number 1. You need to enter a load, and on the right-hand side in the results section, you will basically see for the anchor base plate, you will see the moment utilization and basically the thickness you had there. You had 0.5 inches. You could now go to 1/4 inch or whatever and see until you get to 100% of the moment utilization. In this case, basically, that's how you can do it. In the end, you will also get there a comprehensive report with all the design formulas with all the code references and all this kind of stuff, just to make sure that you can also check it, you can validate it, you have it documented in a proper way, and you don't get stupid questions from building authorities or whatever. I didn't say that this sometimes happens, so I'm sorry. So that's more or less the design guide number 1 functionality. What we have seen, and also in my own experience as a structural engineer, is yes, there are the simplified cases, there are also the cases where you can use your Excel spreadsheet, that's good. But we see more and more that things are getting more complex. Some architects want to have some base plates here very in the corner, or the profile shouldn't be in the center of the base plate, or whatever, right? Things and steel construction is getting more and more and more complex. So what to do in cases where design guide number 1 is not giving a solution? One more thing I want to probably spend 2 or 3 minutes on is this ACI design requirement for a rigid base plate. All this ACI 318, the anchor design guidelines, probably some of you are aware of it. The background of this method is that it's based on a rigid base plate. I got this question probably, I don't know, a lot of times in my 8.5 years. What is a rigid base plate? And until probably 1.5 years, I couldn't answer it. To be really honest, I couldn't answer it. I talked to the writers of the code, I talked to a lot of guys, and nobody really could answer it. So in the end, we thought, there is a requirement in the code, and nobody really knows what it is and how to prove that it's true. So, okay, let's kick off a research project and find or bring some light to the dark, right? That's what we did. And first we started off and say, okay, what might be implications? And this is what I want to demonstrate to you here. If you assume a rigid base plate and you compress it, in the end, the stress distribution underneath your base plate will be constant. Everywhere the same stress. If you now assume your base plate is not rigid, if I push here, you will probably see that underneath the profile, and as an engineer, it makes sense, right? Underneath the profile, you have higher stresses, and at the corner of the profile, you have lower stresses. So if you just kind of assume you're doing a rigid base plate, and your base plate is not rigid, you might underestimate some of the compression stresses. Okay, compression stresses, somebody could say, yeah, not too much of a big deal, because normally the concrete is anyhow not failing, so my gut feeling tells me it will work, right? The next thing is tension. If I pull here, you might see that here at the edges or at the corner, you get these prying forces. As there is deformation here, and basically the anchor is not deforming or only deforming a little bit, the corner will be basically pressed against the concrete, and this will have additional compression stresses. What does this mean? This will, as equilibrium still needs to be there, this means that your anchor forces will be increased. And we have seen cases from customers we got, and the customer did some kind of early finite element model, for example, using robot really shell elements and all the stuff. And there was always, or in most of the cases, a huge deviation. Why? Because of these prying forces. And there were cases where it was not just 10, 20%, there were cases it was really significant, sometimes even doubling the load in worst cases. So this is something, the second topic, in tension, you will have the prying forces, or you might get the prying forces easier if your base plate is not rigid. The third thing is bending. For a rigid base plate, your compression would start here. So you have a triangular or whatever rectangular distribution of the compression, so your center of compression will be here. If your base plate is not rigid, your center of compression will move close to the compressed flange, as an example. So in this case, this means the reduction of lever arm from here to the tension force will change in a worst case from here to the tension force. So in the end, in this case, probably it's a reduction of lever arm of probably a third, means 1.5 higher loads, right? So these are basically the things why it's important to get a feeling on how rigid the base plate is. Questions on that? If I'm too fast, please stop me. Good, silence. Okay. And we talked about cases not covered by Design Guide 1. We talked about rigid baseplate is a theoretical term done by some professors back then when there was no software available, when they had to simplify the reinforced concrete, and the only thing they could do is simplify it in order to be able to do hand calculations. And then the last thing is parameter influencing each other. Let's just say if your profile is now bigger, AISC Design Guide doesn't care about that, how big your profile is. I tell you from my engineering education, I believe if the profile is smaller, you will have more stress in the plate. If the profile is almost going close to the anchor, your base plate will be stressed less, right? So there are a lot of parameters influencing the whole system over here, okay? And that's basically what we wanna now dive a little bit into. Before that, I have another question for you. And I think I have some more knives. The people, that's why you didn't get the second one, right? So I think it's fine. So how do you design base plates in these cases where Design Guide number 1 is not allowing this kind of configuration? If whatever, you really feel that, my base plate, I'm not sure if it's rigid or not. How do you design it in these cases? No? Come on.
Trial and error until you find the design.
Okay. Trial and error with which method? Whatever, some hand calculations, some simplifications, some Excel sheets. Find it? Okay, whatever you can find, just to get a little bit of feeling of how the thing is acting. Okay? Anybody else? You? Yeah, that's good.
Find a gauge for the bolt, that is the space around the bolt that you need in order to get the tool to work, and then just a stiffener place everywhere.
That's a very good. I wanna note that as well, because that's a very good.
So you end up with a rocket ship, essentially.
Exactly. And that's, again, one of the things we are currently working on in order to allow you to put their stiffeners as well. Because as we saw, if my profile or even stiffener, this will stiffen the base plate and my load distribution will change dramatically. Let's just assume I put here a stiffener until here. I can tell you that the load, or the center of compression, will almost move probably to the edge of the stiffener, and from a lever arm perspective, you have probably gained 20, 30, whatever percent, right? That's a very good point. But it's hard. How do you then design the stiffeners?
Take the thickness of the web of the member, just make it either the same or larger.
Yeah,
But
and that's
if it's
again,
by 36, and you need to make it larger.
that's then again, I think, this experience point, or I would call it good engineering practice, or whatever, right? And I think
Really sophisticated.
it's a first step. I think it's good, but still, we believe that there is quite some things you can do better there. And also, then designing the weld, because you will also need to weld the stiffener to the profile, and you will also need to weld the stiffener to the plate, right? So there is quite some stuff that is needed. Let me just check on time. Okay, good. Okay, that's good. Now I will hand it over to David, who will talk about the details behind the innovative component-based finite element method, why it's unique, for which cases it's working, and so on. So, David, the stage is yours.
Thank you, Mario, and thank you, Anthony. Before we will start, I'm a little bit curious, so I have a question. Oh, just now I'm blind. So, how many of you have ever heard about CBFEM? Cool, that's very good. So, let's talk about CBFEM. our unique component-based finite element method. This method allows you to design and code check steel connections and anchoring. In the next slides, we will go through benefits of this method, approach, theory behind the method, its verification and validation, and of course, market acceptance. The CBFEM is quick, efficient, and compliant. The main advantage of this method is that you aren't limited. You are able to do any topology, any loading in minutes, really very fast. There is the main question: how did we figure it out? We thought about weak points of component method because component method is limited in topology. And we merged basis of component method with finite element models, and CBFEM was created. So basically, that's synergy of component method and finite element analysis. Very easy. Very important thing is another question. How does CBFEM work? Let's investigate a little bit more this picture, this diagram. You can perform experiments. You can create exact finite element simulations. But if you want to be on the safe side, you must comply with the code. And that's it. Design-oriented finite element analysis takes into account real behavior of steel joints, of anchoring, and at the same time, it takes into account safety margin. You can imagine it as this area. Let me introduce key features of CBFEM. Each and every part of model has its own finite element component. Plate, member, anchor bolts, welds, and concrete block. Analysis model is created automatically, so without user input. There is no user input needed. So you don't have to be an expert. Everything is done for you in the background. You are just playing with the shape of the structure. Analysis is performed with material and geometrical nonlinearity. Now, let's go through these items one by one. Plate. Plate is defined by shell element. We can imagine it as this base plate. Members are defined from plates. You can see column, and it's created with bottom flange, top flange, and web. 3 plates creates a column. Another component, welds. This item. Weld has its own finite element model which respects geometry, ductility, and stiffness of the weld. One of the best features of that CBFEM can offer to you is distribution of the stress along the weld. So let's clarify it on this picture. You are able to investigate stress in each part of the weld. It's very useful. Then we have anchor model. We can take into account different behavior for anchors in tension and anchors in shear. Anchor material properties are based on experiments, and the stiffness of the anchors is defined by the selected material of the anchor. Then we have concrete block. Connection between base plate and concrete block is able to transfer compression only. The compression is then transferred via Winkler-Pasternak subsoil, which represents the deformation of this subsoil. Tension is carried by anchors, by anchor bolts, and shear resistance is carried by shear resistance of anchor bolt, by bending of anchor, or by friction. Analysis is made as material nonlinear, so it's by default, and delivers stress-strain results for code checks. And as I mentioned before, you don't have to be FEM expert. We are just playing with the shape of anchoring, of steel connection. Yes, here is the stiffener. And from the other side, that's another one. So you are just playing with the shape, and everything, mesh, density of mesh, is done for you in the background. So really, you don't have to be FEM expert. You don't need to use ANSYS, Abacus, or software tools like these ones. One of the very nice and important parts of the CBFEM is its solver. CBFEM Solver has been developed and, of course, verified from scratch. We have used knowledge from other industries, like aircraft industry, where finite element analysis has been used on much higher level over last years than in civil engineering. And let me mention some key features of FEM Solver. Each part you can investigate base plate, and let's say bottom flange of the column. Each part is independent. It has its own mesh because parts are connected by welds or by bolts. And the main thing, or I think the best advantage for you, is the speed calculation, because the speed of the calculation is really fast, I can say in seconds. CBFEM is not a black box. Verification and verifications took a while. We made tailor-made design models which were created in various software such as Abacus, ANSYS, Athena, or Midas FEA. We performed live tests. It took over 3 years, and we cooperate on this with 2 universities. And everything is published and is available online or in our verification book. Just now, we are cooperating with more and more universities all over the world. Let me mention in Switzerland, Germany, Holland, South Africa. So if someone of you here in the audience is from university and you would like to cooperate with us, please contact me after this class. We would be glad. That was about verification, and let me summarize it. What makes CBFEM so unique? The method is really robust and general. It's without limits in topology, loading, design. You are able to do any kind of steel connection, of course, anchoring. And CBFEM powers multiple software tools such as IDEA StatiCa, Hilti PROFIS Engineering, Advanced Design Connection, or Fast Alpine Profile Form. If you are interested in this method, please visit this website, www.cbfem.com, where are a lot of examples, verification, studies, and everything about the background. Or you can contact me after this class or my colleague Martin. Thank you for your attention. And now I can pass the word back to you, Mario.
Thank you, David. Thank you. So just to summarize it, the CBFEM method will take each part of the connection, will model as its own component, which is also the philosophy that is behind all design guidelines for structural steel, right? And as this is pretty complicated and so on, it really helps to move what is already existing in the code for some simplified cases to then with finite elements to kind of generalize it and really make it more robust, and you can apply it for more and more and more cases. So this thing has basically almost no limits, right? Let me come back to this point here. How can you now judge if your base plate is rigid? I told you already earlier that we didn't find anything in any code, and also the code writers couldn't answer the question for us. That's why we did research. And here, basically, I show you more or less what was the outcome of our research. In the class material, we have also some publications and some papers and all this kind of stuff on this method. So if you're interested in more details, you can find it over there. So the main thing is, okay, I have now a base plate for a certain size, and you said, let's start with 1/4 inch, right? In the end, you need now to find out and to get a feeling how far off you're now from the theory, just to make sure that all these possible negative effects don't screw up your design, right? That's basically the main question we want to answer. How do we do it? We have done a lot of research and a lot of tests, and finally we came up with one, I think it's a simple solution. We compare the anchor forces. Let's just assume bending, rigid base plate with reinforced concrete theory and whatever. You can basically say, okay, here is my compression, here's my tension. This is basically then the tension calculated. Easy. Here it's more difficult because without finite elements or without realistic assumptions also on the material side and so on, you won't be able to get these results. So what we are now following, our proposal is, we say, okay, just go here, compare the anchor forces. And we have done that, we have done tests. Then we have analyzed the tests, and then we have tried to find out, okay, until where we can go that in the test we don't see the negative impacts of a really thin base plate. Basically what we have found is shown in this diagram. That's basically is 1.0 is we reached in the test the expected test results. And yes, in testing it's sometimes a little bit below and above, but mean, that's what we have. And then we saw that actually around 10 to 15% deviation in anchor forces, we saw that the tests are really starting to, the load that we could apply on the tests was really starting to decrease. So that's the indication that if your force or deviation on the anchors from a theoretical rigid assumption to the realistic behavior with the CBFEM method, if this is more than 10 to 15, someone could now say 12 or 13, yeah, it's not really sharp, but if it's more than this area, we sometimes could see, for example, if it's twice the anchor force, that's a case I mentioned before, we have seen that only 52% of the load could be carried out in the test. So that's basically, on the other hand side, that's our approach, how we want to make sure that you guys stay in this area where these negative impacts don't really kick in, right? That's the idea behind. And above this nice colorful picture is basically showing you what our software will spit out. On the left-hand side, the theory, rigid base plate. And you can even see it with the distances of the colors changing, right? It's just kind of a very linear approach in the stresses and so on, in the deformation. That's good. On the right-hand side, you see now really the realistic behavior of your selected size, thickness. Anchor bolts play a pretty important role. And then you can compare the anchor forces. In my case here, I have now selected a very thin base plate for this application, and I can show you here that anchor 1 has 58% deviation. 58% deviation, what we have seen in tests, you would kind of see more or less that your design can mainly resist 60% of the load that should be there, right? That's how it works. And yes, there are for sure some cases where you can also apply engineering judgment to go further, right? But we, for the time being, our recommendation is to stay inside this area. If you know more, or if you have a special condition or whatever, and you know that all these negative effects on the anchor design from a non-rigid base plate are not kicking in or are not coming because of this and this, you can for sure go beyond. So the software is open. We don't want to restrict you, but our clear recommendation is if you stay in this window, for the tests we have done, we have not seen a negative impact, right? That's the approach we are going to follow. And again, the article, some publications are available. Good. Why is the anchor also important? Let's just assume probably you guys have seen or used chemical anchors that are really kind of glued into the concrete somehow, right? So these guys are extremely stiff. So you have a very steep load displacement curve, so the anchor will not move a lot if you really pull it. Then you have some sleeve anchors or some mechanical anchors where some sleeves need to be, first it needs to be pre-tensioned or pre-torqued, and then the sleeve needs to go and move, and there is some movement in order to get the load transferred. These anchors have a completely different load displacement behavior. And what we have done is we have analyzed, I don't know the number, but I would say 20,000 tests of different of our anchor products. And for each anchor, each diameter, and sometimes each material or head configuration, so really for each anchor that is available, or for most of the anchor that is available in the Hilti portfolio, we have really looked at done the tests and have really done some validation on this anchor stiffness. Just to make sure, because we're always talking about a realistic picture, right? You want to map what will be there in reality, more or less. And that's why it doesn't help if you just say, okay, I just take the steel stiffness of the anchor and that's safe. That's probably an approach you would take in a robot structural analysis or whatever. We have seen that especially for anchors with less stiffness, you see of the whole connection, you see a completely different behavior. That's why, also I mentioned before, all these combinations of these parameters, that's important. If there are questions, is there a question? No? Okay. I still have, there is a question. Ah, that's good.
I was just wondering, does that work with RAM and RISA?
So what you can do for the time being with RAM and RISA, you can export the loads to Excel, your load combinations. You can put it in our software, and then in our software you can design the stuff. But this whole approach is not implemented in RAM and is not implemented in RISA. That's completely different. These guys are focusing on the superstructure, right? And we are focusing on the detail, on the connection. Okay? You still earn the knife. So that's good. So now, I talked probably now a lot about theory and so on. I want to now hand it over to Anthony, who will really tell you how they at Degenkolb are using this technology and what are their experiences from using the software now for quite some time. So Anthony, the show is yours.
Thank you, Mario. Jump over here out of the blinding light. So a little bit more about some of my background with Degenkolb. So I'm also involved in our analysis standardization in-house effort, and that's a lot of focus on nonlinear analysis and getting that kind of uniform across our firm and across our different offices. So that's a lot of effort on the more superstructure part. But we were really excited to hear about this CBFEM software and being able to use that more advanced cutting-edge approach to our connection design as well. So I'm going to dive into a few practical examples of using the CBFEM software. So this has been a project that's taken over the past couple years of my life. This is a 4-story concrete moment frame structure in the San Francisco Bay Area. And we did a seismic retrofit of the structure as well as a TI. So just a couple of important points just to help make the examples make sense is on the 3rd floor of the structure, the architects wanted to cut in large openings, for some nice light wells, being able to make the space more open. And as part of that, they're putting a LED guardrail system, probably about like 1.5 feet wide, around this whole thing. So that was an interesting design challenge. The other thing is that the gravity system in this structure is precast post-tensioned concrete beams. So those, of course, have their own unique set of issues. And then the last thing is part of our retrofit for the structure was that we added 19 fluid viscous dampers into the building in order to make everything work. Oops, wrong way. Wonderful. Okay, so the first thing I'll talk about is this eccentric guardrail post for this LED system. So we soon realized with this 1.5 feet or so that a lot of it was overhanging off of into the opening, so we couldn't center things where we wanted and would normally want to do it. So in order to hide everything under this, so nobody's tripping around different around the guardrails and the anchor and whatnot, we had to offset the connection. So obviously when you get to something as offset as this, none of your real, you can't use Design Guide 1 anymore. Nothing really works within the bounds of that. So we were excited to quickly implement the CBFEM software on this and really do a comparison between the rigid assumption and then the flexible base plate. And we were able to really justify this with looking at the deformations between the two and saw that even with the CBFEM, there wasn't too much deformation there. It was quite small. So we were able to say, all right, this is probably good enough. And we were able to get much more confidence on our design forces for these anchors. So the second kind of design challenge that we came across was needing to connect our infill steel framing beams to the precast concrete. So the contractor was very quick to say, you want us to drill into tendons? This is going to be a problem. Please, can we do something different? And we're like, all right, so what are we going to come up with? So since these have a nice parabolic shape, the tendons, we thought of, okay, well, all we're doing is having a little bit of gravity load, essentially hanging this beam kind of like that. What if we just put anchors up at the top instead of using our standard kind of 4-bolt connection? But these precast beams have a nice, I shape. So to get that whole cope, we're talking like 4 or 5 inches or so. Really puts some eccentricity into the whole system. So one thing that we again used was the CBFEM software. We were able to say, okay, now that we have this with this nice eccentric moment on the whole connection, what's going to happen? Are we able to really justify, bearing down on the concrete at the bottom, pulling out up with the anchors at the top? Will this kind of actually work, or what's going to happen with that? So again, able to really kind of use this to justify this kind of unique configuration and have a lot more confidence in our response. So the last one I'd like to talk about is trying to connect the dampers into our concrete moment frame system. So as you can probably see from the picture here, all of those lines, horizontal and vertical, those are all of the existing reinforcement in here. So trying to put anchors in that without hitting any of that reinforcement was frankly a nightmare. So the contractor scanned all the different configurations every which way. So you had 19 dampers, 2 ends, each with a column and a beam kind of configuration, all of which were unique and different. As well as needing to put in about 450, 500 kips of force through this whole thing. So quite a lot of fun there. But since we had to avoid all of the different rebar configurations, every single connection was unique. And obviously when you start having weird spacings, okay, these bolts are at 6 inches, these bolts are at 5, now we have the bolts spaced at 8. How is that really going to distribute your forces? You can't really assume anything will work too well that way. So we, again, went to the CBFEM software and really utilized the complete custom baseplate configuration for that. And we were able to model each of our different configurations, see exactly what we needed to do. Do we need to thicken the baseplate in order to avoid prying in some of these cases? What are we really going to get out of these forces? And this, again, helped us really utilize that and efficiently design that whole system. Question, yes? Yeah, so at that point, we split it into 2. So we had one model for the beam configuration, one model for the column configuration, and then as we were looking at it, kind of like fudged a little bit, because obviously there's a lot of stiffness that you get right at the end that we didn't capture. So anytime we saw, big design forces up at this end, we're like, okay, they have this whole other system that's going to help support that. We don't need to worry about, any sort of deformation, too much deformation there. But then again, when it's reversed and going the other way, now, okay, we have, large forces there, exactly what's going to happen. Was there another question on this side? Mario's really excited with these knives. Awesome. So now I'll hand this back to Mario. Thank you.
Exactly. So just looking at now also at the list what we had, right? I think this envelope of different combinations, I hope we could answer this question. I think it was the Revit topic, this ductility, I think I would like to talk to you afterwards to understand this better. This smart tags as well. And then the stiffeners, what also Anthony showed in the last example, and that's kind of a, I'm always trying to, or we're always trying to improve the software and so on. And you talked about stiffeners, right? In one of the pictures, you have already seen that, yes, development is working on it. It's not yet ready because we need to do a lot of testing and make really sure that it's working. But also if you would have kind of the chance to also design this here plus the welds over here, I think this would help, and these kind of cases would be much easier and kind of less customization or less assumptions would be needed. Currently, I think what Anthony said is, yes, cutting this into kind of 2, they were at least able to design it for the different positions of the anchor, which is already a big step, but I really believe there is another step even going forward if we could then also have these stiffener things. So also these stiffeners we talk about. So my question is now for you, and probably some of you can answer, what you have seen. Does this make sense? Do you have already some ideas how you could utilize this for your problems? Because I think the majority or the main reason for this, also for this class here, we want to make sure that we educate, we want to make sure that we bring the concept over, that everybody's understanding it, that we spread the word about these innovative things. Because, if you don't know about it and if you never have heard about it, then it's hard if you run into a problem basically to think about what possible options could be. So is there anybody that wants to basically share if this is useful for your work, or if there could be already some use cases for you in order to design this, or some things might be missing in order to utilize for your case? Please.
Yeah, shear lugs and adding that. So right now, sort of, and this is great, like Pat pointed out, it's always sort of similar to what people have said before. You're sort of using spreadsheets to do half of it, another thing to do it. So our workflow is sort of, design it. If you need a lug to do that, we just go to an in-house spreadsheet, and it just sort of, creates, before you know, you have 5 different files for one single lateral.
Okay. Currently, I can tell you a lot about it. I know we have looked into the topic and it's somewhere in the backlog, but at least I will take a note and then we see what we can do in order to implement shear lugs. Thank you. What else? Anybody else? I think I have one more knife.
So this would be,
You have 2 knives.
this is very useful, very cool. I like it a lot. One thing I would suggest is on your documentation is to have the website or URL linked directly into that documentation. Reason being, I had to do a lot of stuff for the Los Alamos National Labs, and they want validation for absolutely everything.
Yeah. Good.
I would definitely include your documentation there.
So let me just take these 2 things down. So we had the shear lugs, right? Luckily, I hope I can read it afterwards. And then you said documentation. And then here you talk about these papers, you talk about the background behind that. We have a comprehensive package that you can basically attach to your design, that everybody can basically have a look and follow what basically are the assumptions behind and so on. Okay? Anybody else? I'm very proud. I think only one person left the room and 90 minutes is a lot, so that's good. So far, so please don't. So this is kind of the summary slide, right? What we have talked about are mainly 2 things. One is this workflow integration that's now here in the horizontal direction. And in the middle there is the vertical thing where we say, okay, we do now all design checks in one software. As I said before, from Global, we had this question, SAP 2000, ETABS, and actually I forgot to mention the Autodesk product, I'm sorry. Also for robot, we also have this direct integration. From there, you can import the load combinations directly to our software. We have talked for this one to 46, or we have run a survey for 46 structural engineering offices. And on average, what we got is from their current tedious process with doing multiple files to do things like that, basically they reported on average 11 minutes saving for this functionality. As I said before, for all other structural engineering software, that's now the lower line, you can export it to Excel, your load combinations, and then with just copy pasting, you can import it in our software. And that's also what Anthony shared, that these guys at Degenkolb are using extensively, right? Then in the middle, we have, okay, we want to do all design checks in one go. On this one, we did an extensive study. We talked to 531 structural engineering offices around the globe. And what we got there is basically, including all documentation, including all design checks, they reported, or our customers reported, roughly 60 minutes saving by using our software to compare to their old method. For us, it's important that I don't stand here and say, 60 minutes. No, we really have talked to customers, and that's really basically what they have reported. I think that's important. And then the last step is from our software to Revit. And also there for Tekla and Revit, we have these direct connections where the information will be there then as native objects in the software. For all others, we have this BIM CAD library where it's then kind of a block and you can export it to DWG. I think IFC, I think they have 64 different file formats. You can then either in 2D or 3D export it, but it will be just a block with no real intelligence behind, right? On this one, we have talked this case only to 16 companies using Revit, and there we got basically 14 minutes as the average saving. So that's what I want you, if you don't remember a lot from this class, because the party was pretty tricky yesterday, in the end, Hilti has a new software that can do mainly 2 things, a lot of things, but mainly 2 things. Help you workflow integration, saving 20 to 25 minutes on this side, and one innovative design part, which is based on the CBFEM method, that does the whole design for the whole connection for you. These are the 2 main things.
So this is not PROFIS?
This is, okay, good. Let me get to that. So we have a PROFIS Anchor available in the market, I think, since 2009. The software, every year, and I'm responsible for it since 2011, every year it got slower and slower and slower and slower. because we added more codes. At the beginning, we only had ACI 31808. Now we have 11, 14, and very soon there will be 19, right? So we added more and more and more and more things. So the software always became slower and slower and slower. And some standard things like undo button, going back and forth, and such things, we received a lot of, or some complaints from the customer over the last years. So what we have decided now is to build up a completely new software and gradually get rid of PROFIS Anchor, because a software that is 10 plus years old is kind of, from an architectural point of view, technology changed completely, right? And so we have built now the new PROFIS Engineering software, which comes basically on 2 levels. PROFIS Anchor is free. You can design your anchor products, that's great. With PROFIS Engineering Standard, you can do a little bit more than in PROFIS Anchor. You can mainly design the anchors. It's also for free. That's option 1. And then on top of that, we have all this design integration and these innovative things where we invested quite a lot of money. Therefore, we have this premium functionality, which is currently a single license. I think it's priced $20 a month. So the important thing for me always to say is, we believe, and these numbers hopefully show it, that you can save time with it, right? And we didn't want to price it somewhere up in the sky. We believe it's a reasonable and fair pricing, and the feedback we have gotten from most of the, or almost all the companies around the globe that have adopted it already is that they really save much more time, and actually they save money also into their pocket. And we won't, with this license model, I can tell you, we won't make money. I can tell you. The software is running on a cloud service. I can probably forward you the Amazon hosting costs and so on, right? So it's an expensive thing, but we really believe we want to help you in order to gain productivity, because we see in our industry, in the design process, there is a big lack of productivity, and we want to partner up with you, and we want to bring this productivity. Is this answering your question?
Yes. Question.
Yes.
Is it just single licenses at this point?
No, we have also floating licenses available, basically, that, yeah, there are certain license options available. If you have more questions, we also have a booth, so please walk by, and if you want to get a demonstration or whatever, just come by and we can show it to you, or answer then some more questions if we would run out of time. So now it's tricky. I only have 1 knife left. You already have one. Okay, that's good. Then we start with you. Okay.
Thank you.
Sorry. Exactly. That's true. Thank you, Jennifer.
So on the slide, I saw that the concrete element is modeled as the compression frame. I wonder how that fit with the ACI 318 in terms of the concrete breakout and all that stuff.
This is, okay. So there are 2 things we need to distinguish. Actually, a very, very good question.
Because, I mean, the CBFEM, from the material standpoint, all the column, base plate, well, angle of that, it's much more ductile compared to concrete.
Yes.
So I wonder, would you capture that concrete failure mode, failure plane, and things like that? How you take that into consideration?
So currently the concrete is modeled as these springs, and these springs are in compression, right? So all the design checks for the anchors are done according to ACI 31811. So with the finite element models, we basically get the anchor forces, and then these tension breakout cones and the shear breakout cones are done by the concrete. So we are not yet there that we can, because concrete is hard to model, cracks, rebar, whatever, that's pretty tricky. So we are far away from that. We use this methodology in order to make sure that we design the steel part in a proper way, and then we transfer the anchor forces and compression via compression, right, to the concrete, and then the anchors are designed by our ACI 31811 or 14 or whatever, and the concrete is also being designed for this compression, colorful pictures over there according to the code.
The only thing that you ship on concrete based on this approach is that basically the compression on the concrete spring.
Yes.
Everything else is from the anchor force.
Exactly.
Back to the create.
Yes. Yes. Probably in 5 years or whatever, we will be also able to do realistic concrete cone finite element simulations. I can tell you in our research and development departments, they have software packages to do this, but I can also tell you that this sometimes runs a week, right? So it's tricky. It's a different magnitude, and that's also what David showed. There is the design-oriented finite element, that's what we're using here, and then there is the thing to really do experiments, and there you would really need to go into much more non-linearities. Okay? Thank you. There was one more, yeah?
Does the program have the ability to use existing cast-in-place anchors and supplemental post-install anchors in the same application?
So we have the ability to use cast-in anchors as well. So for the time being, it's only available for anchor design with this kind of, I don't care about the base plate, I just assume a rigid assumption and that's it, like in the past. We are working on to bring the cast-in-place anchors, the stiffnesses of these cast-in-place anchors also into this CBFEM model. But there we will stop. So we won't be able to mix different anchor bolts in a base plate because it's not allowed per code. As per ACI 318, no, 08, 11 or whatever, you're only allowed to have the same anchor types, not even different diameters, not even different post-installed anchors for one base plate. Reason for this being also stiffness of the anchors and so on, that this is really currently the design framework cannot control this, that's why it's not allowed. Okay?
Wells and bolts resistant the same force, right? Two different anchor types would be like having wells and bolts trying to resist the same shear. The well's going to be stiffer than the bolt. It's going to take the...
Yeah, but
Yeah,
just if you have just centric tension, right, and you have 3 anchors kind of, let's just take the model over here. If you have 3 anchors, let's just assume cast-in anchors, and then you put there 1 post-install anchor. Basically, all the assumptions behind the code is that basically the anchor stiffness of all these anchors is the same. So then the question you would need to ask is, okay, in which direction is my bending? Which of the anchor is kind of now the one that has a higher, lower stiffness? So then it really gets complex, and most likely on the job site, whatever you design, most likely on the job site, it will be anyhow screwed up, right? So that's why kind of the code is not yet there. In future, it might be a thing that can be covered, but for the time being, it's not. Okay? Good. Then I have one more slide, and we are here for questions. So it's just kind of a nice picture, and probably you guys have seen already these robots that are walking around and things like that. So that's basically just our vision, how construction will change going forward, and probably you can see already some kind of robots we have already put together some years ago in our vision, but that's just our vision, how we see the construction changing. Thanks a lot for your attention. Thanks a lot for being here. Again, we will be available here for some more minutes, and otherwise we will be available for your booth. Hope you enjoyed it. Hope it was helpful for you. And in case of questions, please reach out to us with whatever channel. We're happy to help you, okay? Thanks a lot. And thank you also, Anthony and David, for helping me out with some more realistic examples and some more in-depth expertise. Thank you.